We've always used maps to understand our world. But what if we could map something you can't even see? Today, we're diving into the incredible new blueprints that humanity is creating to chart the unseen. Everything from the deep ocean to the inside of our own minds.
Seriously, how do you do that? How do you actually draw a map of a thought? Or figure out how an animal can feel its way across thousands of miles of empty ocean? For a long time, these were just, philosophical questions. Not anymore. Now, they're engineering problems. And researchers are building these absolutely incredible new kinds of blueprints to explore these invisible worlds. We're going to look at 4 amazing examples today: how we're preserving ancient history, decoding animal instinct, mapping a living brain, and even designing a cleaner future in space.
All right, first up, a true masterpiece of stone and faith, St. Peter's Basilica. It's a 400-year-old treasure, but of course, time and the elements are starting to take their toll. So the big question is, how do you preserve something like that forever? Well, turns out you create a perfect digital copy. To pull this off, a team from Iconem and Microsoft took on a monumental task. Get this. They captured over 400,000 high-resolution images of the Basilica. Just think about that number for a second. That's a data set so massive, they actually had to develop new technology just to process it all. So how did they actually do it? Well, first, they spent 3 solid weeks scanning the entire building, inside and out, with everything: drones, cameras, lasers. Then Microsoft's Azure AI took that mountain of images and started piecing it all together. The final step was to build what they call the digital twin, an incredibly precise 3D model that's accurate down to the millimeter. And this isn't just some fancy 3D picture. As Iconem's founder, Yves Ubelman, said, it's much more than that. It's a digital blueprint that lets us investigate history itself, to see how the building has changed over time, and even spot tiny vulnerabilities like cracks that are completely invisible to the naked eye. Okay, so from charting ancient stone, let's switch gears to charting something alive. Let's talk about instinct. Specifically, the incredible mystery of animal navigation. How does a tiny little loggerhead turtle hatchling start an epic journey across thousands of miles of ocean and somehow know exactly where it's going? Scientists were pretty sure the turtles were using the Earth's magnetic field as a kind of map. But the big question was how. Were they using a light-based sense to somehow see the field? Or were they using tiny magnetic crystals in their bodies to literally feel it? To find out, researchers came up with this really charming experiment. I love this. One of the scientists, Elena Makovich, explains how they trained baby turtles to connect a very specific magnetic field, the one right around the Turks and Caicos Islands, with getting food. And whenever they recognized that field, they'd do a little dance, opening their mouth and waggling their flippers. It was their "feed me" signal. And then came the critical test. The scientists exposed the turtles to a strong magnetic pulse, which temporarily messed with their ability to feel the magnetic field. So what happened when they put them back in the food zone? The dancing stopped. And that was it, the proof. The turtles weren't seeing their map, they were feeling it, using an incredible internal compass. All right, so from a biological map written in instinct, we're now jumping to an even more complex system, one written in pure electricity. This might just be the most ambitious blueprint of them all, a complete wiring diagram of an adult brain. And the subject? A fruit fly. This kind of map is called a connectome. It's basically the ultimate electrical blueprint, showing every single neuron and every single connection or synapse between them. And why does this matter so much? Because if you can map that fundamental circuitry, you can start to understand how incredibly complex things like memory, behavior, or even thought itself actually emerge from all those connections. The sheer scale of this is just staggering. The project, called Flywire, started by reconstructing every single neuron in the fly's brain, all 139,255 of them. But the neurons were just the beginning. They then had to map every single connection between them. In total, they charted over 54.5 million synapses. To put that into perspective for you, if you could stretch out all those pathways end to end, they would be 149 meters long, and all of that is packed inside a brain smaller than a single poppy seed. That is an almost unimaginable density of information. For our final blueprint, we're going from the inner space of the mind to outer space, and we're looking at a huge problem we're creating for our own future.
that growing cloud of space debris that's orbiting our planet. You know, every satellite we launch eventually turns into another piece of high-speed junk orbiting Earth. But what if we could design them to be temporary? What if a satellite could just vanish? Safely, of course, once its job was done. See, when a normal satellite re-enters the atmosphere, it burns up, but it leaves behind these tiny metal particles that can just hang around for years, and that could potentially harm our environment and mess with telecommunications. That's the problem researchers at Kyoto University decided to solve. Their solution is called LignoSat, and it's just beautifully simple. It's a tiny 10-centimeter cube made almost entirely of wood, a wooden satellite. The idea is that when its mission is over, it'll just re-enter the atmosphere and burn up completely, leaving nothing behind but a little bit of harmless ash. As astronaut and Professor Takao Doi says, this could be the blueprint for a whole new generation of space technology. The LignoSat was successfully launched, and if it proves it can survive in space, it could completely change how we think about building for a sustainable future beyond Earth. So there you have it. From a 400-year-old church to the brain of a fly, we've looked at 4 totally different problems, and all of them were solved by creating a new kind of map. We've explored a digital blueprint to preserve our heritage, a biological one to decode an animal's inner compass, an electrical schematic of thought itself, and a sustainable plan for our future in space. Each one of these is revealing a world that until now was totally invisible. By creating these new blueprints, we're learning to see the unseen and chart the unchartable. So the only real question left is, what invisible world will we decide to map next?